In this lecture, we will learn about the biocompatibility of plasma sprayed carbon nanotube reinforced hydroxyapatite bioceramic coating. So, in this particular case, we are utilizing hydroxyapatite, which is a bioceramic material with some certain reinforcements of carbon nanotube to perform a superior material with a biocompatible nature, and this particular material has been synthesized using plasma spraying to form it as a coating. So, in this particular lecture, we are seeing hydroxyapatite, which is being reinforced with carbon nanotube, and since it's a we are just going to check its biocompatibility, and this material has been sprayed, plasma sprayed, to form a coating onto an implant material. Because we realize that certain biometallic implant material don't have good wear resistance. At the same time, they sometimes underperform as a good compatible material with the surrounding tissues. So that is the reason there is a need for producing a coating onto an implant surface so that the overall performance of the implant can be enhanced. So hydroxyapatite has been well known as a very important material. It is described as Ca10 PO4 OH twice. So it is a apatite structure which is a calcium by phosphate ratio similar to that of bone, which is approximately 1.667. So that hydroxyapatite is well known biocompatible material with Ca/P ratio of 1.67, and now this material has been plasma sprayed with and without the carbon nanotube, just denoted by CNT. Hydroxyapatite is a well known bioceramic. Hydroxyapatite, the chemical composition of hydroxyapatite is given as Ca10 PO4 OH twice. So hydroxyapatite is a well known bioceramic with a calcium by phosphate ratio of 1.67. As we see, the Ca is around 10, P is around 6, so 10 by 6 it becomes around 1.67. So this particular Ca/P ratio is similar to that of which is found in the bone mineral, which is apatite, similar to that of apatite. It is also 1.67. So we see that hydroxyapatite is the ceramic part which is available with the collagen, and then therefore hydroxyapatite is considered as a bioceramic material which is much more compatible with the body itself. And then this hydroxyapatite HA is being plasma sprayed with and without carbon nanotubes. Again, carbon nanotube is denoted by C and T, and consequently I'll elicit more of the macrostructural and the mechanical analysis of how and what these CNTs are contributing, followed by the cell culture studies in order to say whether hydroxyapatite is getting compatible once we are adding carbon nanotube as a reinforcement. So we know that hydroxyapatite is a biocompatible ceramic with as we saw that Ca/P ratio is 1.67, and this bioceramic, it has chemical nature very similar to that of a bone and the teeth material. So that forms a mineral part of our bone and teeth, that is nothing but apatite. And coming to it, the microstructure can also have very dominating effects. The kind of crystallinity of hydroxyapatite can also alter its properties. Also the kind of phase which are being generated after the processing can also impart very different properties to the hydroxyapatite. It can also lead to some degradation of phase, the percent of crystallinity. Also the kind of phases which are being generated, those phases can be degradable, those can be non-degradable. So we need a proper combination of those phase compositions in the hydroxyapatite even after processing. And but the basic problem with the hydroxyapatite, it is a ceramic and therefore it is very brittle. Its fracture toughness is to the order of 1 megapascal root meter, which is very poor. So we often see that the ceramic, once we drop it, it basically breaks. So we take a ceramic hydroxyapatite, we tend to drop it, it will basically break. So to enhance its mechanical properties, to enhance its fracture toughness, we tend to add carbon nanotube. So we add carbon nanotube in order to increase its bend strength and the fracture toughness. So fracture toughness is a key part in terms of adding the reinforcement of carbon nanotube. But again, carbon nanotube, it is said there are two school of thoughts, that carbon nanotube is nothing but a graphitic layer, a graphitic sheet which has been rolled as a tube, and the diameter of this tube is to the order of couple of nanometers. So there are two school of thoughts. One group says anything nano is deleterious to body because it can penetrate through cell walls, it can get accumulated somewhere, and then it is highly deleterious for the body because we cannot take it out, we can't even see it so nicely. So how will we take it out, and it will just get clogged into some location of the body. So it can induce some toxic effects. But the second school of thought, basically it comes out from the truth that carbon is the basic form of life. So why anything which is carbon in nature, like graphite, why it should be deleterious to the body? So there are two counter arguments which are so much nice, which are very highly reported in the literature, that carbon nanotube, it is toxic and it is non-toxic. But people do have seen some effects of irritation or toxicity, whereas other group also have seen apparent precipitation onto the carbon nanotube surface. So these we have to carefully weigh these two particular aspects before we really take them for clinical trials. So ideally we are adding carbon nanotube as a reinforcement in the hydroxyapatite to improve its fracture toughness. We also need to confirm whether these scaffolds will be toxic or will be cytocompatible. So we need to take that part also in consideration. And ideally these coatings are done on the bioimplant material, because we realize that the titanium 6 aluminum 4 vanadium implants, they have very poor wear resistance. Also also if you have a ceramic coating onto it, we can increase its biocompatibility, we can also increase its corrosion resistance. So we can see that by inducing certain coating to it, by providing certain coating to it, we can improve its mechanical properties. So we can improve its wear resistance, we can improve its chemical properties, we can improve its biological properties. So that is the overall concept behind performing a coating onto the implant material. And in the plasma spraying, we utilize a hydroxyapatite powder, which are more than 99% pure. And plasma spraying requires that we have powders which are approximately 10 to 50 micrometers in diameter, which can be irregular or spherical in shape, that does not matter, but ideally they should be 10 to 50 micrometers in diameter. If they are very fine particles, they may not be able to overcome the bow shock, like, because if a particle is flowing, it needs to overcome a certain shock. If something is getting impacted onto a substrate, so there will be a bow shock and the particle has to overcome that particular shock, so they have to be of a particular size. But on the other hand, if they are very huge in size, the surface will not melt at all, because all the heat will be utilized in melting the surface, but that heat will not be sufficient to melt the particle, because it has to cover a very short distance in a very short time. So the particle will not stay in the plume for longer time. So larger particles also face a problem and smaller particle also face a problem. So that is the reason ideal range is around 10 to 50 micrometer of diameter. So that particular powder particle has to be utilized in terms of plasma spraying. Followed by it, that we also need to disperse the carbon nanotube, because carbon nanotube is a very fine particle, like a fine tubular structure. So because of its very high surface area, they tend to be very unstable, and then they tend to agglomerate with one another. So that is the overall thing behind it. So we need to disperse some of these carbon nanotubes and disperse them in the hydroxyapatite matrix, so that we can utilize the CNT, individual CNTs, in terms of taking the basically extracting the superior mechanical properties. CNTs have a elastic modulus to the order of 1.4 terapascals and a fracture strength to the order of gigapascals. So that part we want to utilize in terms of basically adding them as a reinforcement, and then once we have them as reinforcement, then we can achieve a overall very good implant with a very superior coating, and the overall performance of the implant will go drastically high. Plasma spraying, how does plasma is nothing but plasma is the ionized gas. So we have ionized gas that is being struck as an arc between the tungsten cathode and the copper anode. So we strike an arc between the tungsten cathode and the copper anode, which is out here. So we see the copper anode out here. So an arc is struck between them, and that arc basically leads to generation of plasma, because we supply a gas which can be argon, and that argon passes through this particular arc, and it gets excited to generate the plasma. So we see this plasma out here, and then we feed the particle. So we feed the powder particles through this one, and we insert it in the plasma plume, and we accelerate these particles via some carrier gas. So we have plasma temperatures in excess of 10,000 Kelvin, and we are feeding these powders into the plasma, and we are accelerating these particular powders to supersonic speeds via some carrier gases. And once it impacts onto this particular surface, in this case we have titanium 6 aluminum 4 vanadium substrate. So in this particular case we have titanium 6 aluminum 4 vanadium substrate, and then we are basically depositing this particular ceramic coating, which is hydroxyapatite CNT. And ideally these powders, HACNT powders, are being blended. They have been ball milled, they have been milled, blended in a jar mill, and then we are seeing that this CNT powders are just getting spread out by itself. So that is the overall deal with it, that the plasma is the ionized gas through which we basically feed the powders in the plasma plume, and they are accelerated to supersonic speeds. It is more like playing with the water balloons. So we are taking a water balloon and then we are impacting it onto a surface. So there is a kind of a layer by layer deposition which really occurs via this particular processing. So we have a powder particle, it is accelerated because of the carrier gas, it is taking it, and then it passes through the plasma, surface gets melted and the particle becomes morely molten or semi-molten in nature. Then once it is impacting the substrate, it forms a splat, and then consequently or successively another splats, another molten or semi-molten particles, they get impacting onto the substrate, and from that we develop a coating. So that's how we see a deposition technique is being utilized in terms of creating a graded kind of a structure out here. So we see that once it is impacting onto the substrate, it undergoes rapid cooling, and that forms a coating on the titanium 6 aluminum 4 vanadium substrate. So ideally the coatings look more like this. We have a molten or semi-molten particle, then it basically goes onto impacting the particular substrate, and it splashes out like this, and we have successive deposition will lead to formation of coating. So the coating looks more like lamellar in structure. So we have lamellase, and then we have this particular substrate. This is a substrate, and we see the coating which is being deposited like this. This is coating. So this is what we are seeing, that we have a stream of powder particles which keeps impacting onto the substrate, and then we have all the molten semi-molten particles. This is a plasma plume, and upon impact onto the substrate it forms a coating. And coating with and without CNT, ideally the hydroxyapatite is more whitish or grayish in nature, so the overall feel of this particular coating will be much more lighter or the grayish, like lighter grayish in nature. But once we add carbon nanotubes are much more blackish in nature, and what we see is that we are achieving total kind of a black coating. So we see totally blackish coating. Once we are blackish coating will be appearing once we add carbon nanotubes into the particular material. So that's what is being observed for the plasma sprayed coatings, that first of all they form a lamellar structure, and then coating is much more there is much more difference in color because of the inherent nature of the hydroxyapatite and CNTs. So that's what hydroxyapatite coatings appear much more grayish or light off white in color, whereas HA plus CNT coating will appear much more blackish in color because of the CNT content in out there. So that is the overall thing which we see out here. And again the X-ray diffraction will also come out to be it will show all the peaks of our hydroxyapatite. It has certain peaks of hydroxyapatite, we will see certain peaks of hydroxyapatite, but at the same time for the hydroxyapatite, if you are seeing something like this, since CNT content is so small and the hydroxyapatite peaks are much more stronger, we will see approximately similar coating with similar kind of peak. This is 2 theta, this is the intensity. We will see peaks at similar locations even for once we have hydroxyapatite with some CNT reinforcement. So we have HA plus CNT, it will show the similar peaks, but the difference will be that hydroxyapatite itself will have poor crystallinity because they don't get much time they don't get much heat in terms of in achieving a slower cooling. So they tend to get amorphous because the cooling in the plasma spraying is to the order of 10 power 6 kelvins per second. So with such high cooling rates, it is very easy that some amorphous structure can also get generated. So ideally we see some broadening of this particular peak in hydroxyapatite. So this particular regime out here will be which will have very huge background, it will show very wide widening of this particular peak at certain location. So we see too much widening in hydroxyapatite XRD pattern, whereas once we have carbon nanotube, we see much sharper peaks. For the same locations. This particular broadening tells that the structure is much more amorphous in nature. With hydroxyapatite, but this HA plus CNT, it's much more crystalline in nature. So we see 2 theta along this side, intensity along this side. So we see that this particular structure is much more hydroxyapatite is much more amorphous in nature, whereas hydroxyapatite plus CNT is much more crystalline in nature. and that happens that clearly tells that there is something with respect to CNT, and that is the reason you are seeing much more sharper peaks, or the crystallinity part is being dominated by the CNT itself. So first of all, we can directly say there is some difference in crystallinity is coming out with respect to CNT, and secondly, there is much more amorphous content in the. Say that there are some secondary peaks which also generate out. So there can be additional peaks as well. There can be tricalcium phosphate, there can be amorphous calcium phosphates, calcium oxide. All these species can also generate in any processing. But in the plasma spraying, the process is so rapid, we can just see either TCP phases, which is much more amorphous in nature. So we can see that this particular structure is being dominated by presence of CNT. That CNT is responsible for inducing those crystalline peaks. And secondly, there can also be some effect of in terms of the sharper peaks. They are not the CNT peaks are not really being observed out here. And secondly, the crystallinity part is also being dominated by the carbon nanotube content. And as we see that the processing can also induce some different peaks, which can be tricalcium phosphate, amorphous calcium phosphate. Those can even be calcium oxide. But what we are seeing in this particular spectrum is there is no presence of any other secondary peaks, but there can be also presence of certain TCP peaks because of the rapid kinetics which is involved in the plasma spraying. So we can also observe some TCP peaks that will induce certain amorphous structure or the amorphous nature in the particular coatings. So ideally, we can see that the crystallinity which is being induced, that can be calculated by the area under the particular peaks. So we can see that the area under this particular peak can provide us the overall content of this particular or the crystalline nature of this particular peak. And we can also see that the and if we take the peaks which are much more amorphous, so we can see there will be a broadening of the peak. So the amorphous nature can also be deducted from there, and we can find the crystallinity is only the crystalline peaks divided by the total area, and that area comes out to be around 50% for only half, whereas it comes around more than 80%. So we can see that this particular values are around more than 80% for hydroxyapatite plus CNT. So that tells that clearly CNT is playing a part in terms of increasing the crystallinity of this particular structure. So that is what is so critical about this part, is that CNT serve as certain sites for supplying some additional heat to the hydroxyapatite and then making it much more crystalline. So letting it crystallize for a longer duration of time, because once the plasma spraying is being done, the whole powder stays in the plasma plume for a couple of microseconds, and that time is not sufficient for the hydroxyapatite, and again it undergoes very rapid cooling to the order of 10 to the 6 kelvins per second. So they don't have enough time to get crystallized again. Once they have heated to very high temperatures, they tend to get amorphous, and then once it is nothing but liquid or solid, semi-solid state, and when it is cooled so rapidly, it does not get time to crystallize itself. So somehow CNTs are playing a part in supplying that additional heat and letting it stay hotter for longer time, and that is allowing to reduce the cooling rate and then achieve much more crystallinity of the hydroxyapatite in presence of carbon nanotubes. And at the same time, we don't see any CNT peaks in the X-ray diffraction, because the overall hydroxyapatite peaks are much more dominating, and depending on the concentration of CNT, they may not just appear. So that is the overall deal with the X-ray diffraction. Secondly, we can also see that secondary phases such as tricalcium phosphate, amorphous calcium phosphate, calcium oxides, or even titanium oxide can also get generated out here, depending on how much if surface itself is also getting oxidized or getting exposed to high temperature. So generation of secondary phases or other phases becomes inherent. So we can see tricalcium phosphate, tetracalcium phosphate, amorphous calcium phosphate, calcium oxide, etc., which can also get generated during the processing. And again, if you are seeing all those phases, it is nothing but the degradation of this particular coating. So the degradation should not happen during the plasma spraying. And again, once we have this particular degradation, it will deteriorate the mechanical properties of the coating. And again, if we start having certain bioabsorbable or the amorphous phases, they will dissolve with time, and then that will weaken the coating structure. So we can see if we have certain structure, it can form maybe like platelets kind of structure can form within the matrix. So if we have some hydroxyapatite matrix, we can see formation of tricalcium phosphate as platelets. And again, if we are making some reinforcing structure such as an implant, and if we start seeing that the sites are getting loosened up or they bend, or some structures we are losing certain material at from certain location, it is basically not good because it is getting disintegrated and it is structurally unstable. So that thing should not happen. So that is the reason we want to maintain or control the dissolution of this particular implant. So we need to have a very controlled degradation of the material. So even when we want degradation, it should be much more controlled in nature, because if we want the bone to take bone to fill up the particular material, the material should start degrading from the surface, and then bone should take place of that particular dissolved surface in order to achieve a good bonding with the implant and the surrounding tissue. So this is the tissue which can basically replace the surface and then basically take the place of the implant. So even if we want a degradation, we want to have a very controlled degradation, and if we have some secondary phases which are being generated into the material during processing, that is not good, because that will make the structure highly unstable and we cannot utilize that as a weak coating structure onto the implant material. So what is happening in presence of CNT? First of all, we have a hydroxyapatite crystal which is basically molten, and then it impacts onto the substrate. It undergoes a rapid cooling, because cooling in the plasma springs to the order of 10 to the power 6 kelvins per second, and then in absence of CNT, basically hydroxyapatite does not have enough time because of its lower thermal conductivity, which is to the order of 0.72 watts per meter Kelvin. It is not able to generate enough heat in itself so that it can pass it on to the center, or so that it can collect the heat at the center or the core of it. So obviously only the surface gets heated up, only the surface will get heated up, and then it will basically cool down once it's impacting with the substrate, and it achieves a very low crystallinity, because once it is impacting on the substrate, it is forming a thin splat. So its thickness is very, very fine, and so most of the surface is basically devoid of the heat. So this heat is being released to the substrate very quickly. So it is not finding enough time to heat up itself. At the same time, it gets released very quickly in absence of any CNT. But in case of CNT, what happens? That CNTs, they absorb very high heat, because the thermal conductivity is to the order of 3 orders of magnitude higher than that of a hydroxyapatite. If hydroxyapatite is around 1 watt per meter Kelvin, CNT will have thermal conductivity order of 3 orders of magnitude higher, 3000 watts per meter Kelvin. So what happens? During heating process, CNT will absorb most of the heat. Once CNT has absorbed most of the heat, it will acquire enough heat that it can transfer it back to the hydroxyapatite once it is even being impacted onto the substrate. So now hydroxyapatite, once it is impacted onto the substrate, it will start getting heat from the CNT, and now it will get enough time to get crystallized, because now some heat is being supplied to it from CNT. So CNTs keep giving heat to it, and then it basically achieves very high crystallinity. So that is the difference once we have hydroxyapatite with and without CNT. In case of without CNT, it basically undergoes very rapid cooling, rapid order of 10 power 6 kelvins per second, and it induces very low crystallinity into the material. But once we have carbon nanotube in presence in near to the hydroxyapatite splats, because of the higher thermal conductivity of CNT, which is to the order of around 3000 watts per meter Kelvin, it captures much more heat while it is in the plasma plume. So once it has very high heat available to itself, so while cooling, it can impart the same heat back to the hydroxyapatite splat, and that heat can be captured by hydroxyapatite splat to basically start precipitating itself again as a crystalline material. So that amorphous part is basically again lost, because it is now undergoing a lesser cooling rate. The cooling rate is not as drastic as it was in absence of CNT. Now because of CNT, the overall cooling rate has been decreased, because CNT itself has so much heat that it keeps giving it to the hydroxyapatite surface, and that released heat basically is being captured by hydroxyapatite to induce crystallinity in the hydroxyapatite, and we can achieve higher crystallinity, which is the order of around 80%. So we can see this difference, that CNT is inducing this crystalline effect and increases it from around 50% to approximately 80%, and this is all happening during the plasma spring of hydroxyapatite. So the duration time is less than a microsecond, or approximately few microseconds, or less than a maybe little couple of microseconds or less than a millisecond, and the duration time is around 10 to the power 4. It's around the dwell time of this particular particle in the plasma plume is around 10 power minus 4 seconds. So it is less than a millisecond. So that is the duration of time we are talking about out here. That time should be sufficient for the CNT to capture the heat and release it back to the hydroxyapatite in a certain longer duration. So this time is only available for hydroxyapatite to either absorb heat during the plasma plume, and once it is basically settled onto the substrate, it does not have any heat left in itself, because all the heat is being lost to the substrate. Whereas in presence of CNT, this time is approximately sufficient for itself to get heat, to absorb enough heat, and then once it is impacted onto the substrate, it can release that particular heat back to the hydroxyapatite crystal, and therefore the overall crystallinity can be increased drastically high. And the overall idea behind increasing the crystallinity of the hydroxyapatite is that we achieve a stable structure which does not degrade with time abruptly. So if we have certain phases, different phases which are being evolved, so those, once they start degrading, they will weaken the overall structural integrity of the whole implant. So in this case, we can get a much more control over the structural implant, that we know that this structure will not degrade with time, and we can design accordingly. And again, the CNTs, they have to be distributed. So if we are seeing a particular structure, we have hydroxyapatite and we have CNT which are all agglomerated, because CNTs are nothing but a diameter of around 40 to 70 nanometer for the double walled for the multi-walled CNT, and if they are agglomerated, it makes no use, because they are all agglomerated and we can't take advantage of single nanotubes, of individual nanotubes. So that will create a problem, because once we are not able to capture the advantage of a single nanotube, that doesn't make sense. So we need to have a structure which has much more distributed CNT. So we had CNTs throughout the matrix, that will give out much better properties. So all CNTs distributed CNTs will give out much enhanced mechanical properties. So that is what we are really looking for. And because owing to the very high surface area of carbon nanotube, they tend to basically agglomerate. So that agglomeration has to be avoided in the first stage itself, that is the blending of powder. So if you are utilizing a powder which serves as a feedstock for plasma spraying, if you want to avoid the agglomeration, that has to be avoided in the blending stage itself, that we take powders, and then we take powders of hydroxyapatite and then we mix it with CNTs. So CNTs basically should get dispersed in the powder formation itself. So in the powder feedstock itself, we should have dispersed CNTs in the matrix. So we should have CNTs which should have been dispersed out here in the powder stage itself, and they should not get agglomerated later on in the coating. So if we have all the CNTs which are all entangled in the coating, that is not good. So that is not good. But once we have CNTs which are all distributed in the matrix, like here, here, here. So if we have CNTs which are distributed throughout the matrix, that will be very, very good. So to do that, we need to have the CNT dispersed much at the ball milling, the blending stage itself. That once we are blending it, we need to disperse the CNT in the hydroxyapatite matrix. So if we are able to achieve this particular blending in hydroxyapatite itself, that same particular phenomena we are thinking that it will get retained even after plasma spraying. So this thing becomes highly essential, that we are able to disperse the carbon nanotube in hydroxyapatite matrix at the stage of blending itself. If you are not able to achieve this particular blending and dispersion of CNT during blending, then the agglomeration of CNT will remain even during this plasma spraying process. So once we are blending it, we should be able to have dispersed CNTs. Otherwise this particular agglomerated CNTs will remain even at the plasma spraying level. So we need to avoid this particular structure, that we should not get agglomerated CNTs even in the blending stage. But one more problem with this distribution of CNT is that this particular structure is good. So we need to so if CNTs are there on the surface of the particular hydroxyapatite surface, it can also induce certain toxic effect as well on the surface. So we need to also take care whether these CNTs are forming a toxic surface or not. Same time, we need to see the dispersion is increasing the fracture toughness part or not. So those all are the essential components to discuss whether we want to have CNTs distributed, and then we are able to achieve their toughening from it. So CNTs, once they are distributed, they can provide very nice anchoring. They can provide a splat bridging. It means in the structure, plasma spread structure, once we are fracturing the particular material, we will have one splat like this, one splat like this, splats like this. They can get anchored by a CNT surface. So if we have a CNT surface, we can see this particular anchoring which is being done by the CNT. So we have CNT like this. So because of their exceptional mechanical properties, which are, because CNT is a modulus of around more than 1 terapascals and fracture strength of around around 100 gigapascals. So CNTs can be very strong in terms of reinforcing this hydroxyapatite splats. So if we had this particular hydroxyapatite splats, so this was hydroxyapatite and all this is CNT. So we can, if CNT is forming a kind of bridge between the two, it will anchor at these two locations, and once these splats are getting separated far apart, it will form a bridge. So we have HA, hydroxyapatite, we again have hydroxyapatite, and once we are applying certain force to separate them, CNT will act as a bridge. So we have CNT bridge that will basically induce much more toughening to the particular material. Because the modulus also is very high for CNT, and pressure strength is also approximately 100 gigapascals for the CNT. So that particular toughening is being given by the CNT. Additionally, CNTs can also serve as a crack deflection part. So if we had CNT somewhere, if we had some CNT somewhere, then if crack is really flowing, once it encounters a CNT, it will get deflected. Because of its higher mechanical properties, CNTs won't allow the crack to proceed further. Additionally, they can also provide certain reinforcements. If the crack is propagating like this, and we have CNT which is approximately like this, then this particular part cannot grow further, it can get separated further, because we have CNT out here in this particular regime to take care of the, if we have CNT out here, then it basically is bridging the or pinning down the crack. So crack pinning can also be assisted by the CNT. So that part also can be taken care by the CNT. So we have splat bridging, we have crack pinning, we can also have something called crack deflection. So once a crack is really flowing or propagating, then it can encounter a CNT and then it can get deflected. So CNT surface also help in deflecting the crack. So eventually crack has to take a longer path. Once it has to go from one end to another end, it has to take a much more tortuous path and longer path. So that basically again makes the crack to flow with much more difficulty, because had a crack been propagating straight, it is not facing any obstacle, but as soon as it interacts with the CNT, it has to flow in another direction. So now it is very difficult for the crack to come back to this particular stress state. So now much more energy is being absorbed in terms of deflecting the crack and then making the crack come back to its original line of propagation. So it is inducing basically much more, it is inducing much more energy, it is requiring much more energy in terms of propagating the crack. And so that is the reason how CNTs can improve the fracture toughness via splat bridging, via pinning the crack, also via crack deflection, and providing a contour or a tortuous longer path to the crack. So these all are the mechanisms by which the CNTs can anchor the hydroxyapatite splats. First, by splat bridging, that it can bridge the splats, it can act as an anchor. Secondly, it can also provide crack deflection. It can also serve as crack pinning location. It can also provide much more tortuous nature to the crack via its deflection. So now crack has to take much more contoured path to come back to its original location and then propagate further. So these are all the mechanisms of toughening via carbon nanotubes. So if we see it more like this, that we have hydroxyapatite splat, so we have splat out here, and then CNTs are basically bridging the two splats via forming certain anchors. So we have one anchor out here, one anchor out here, and once we supply enough force to it so that it basically fractures at this particular location, the top portion looks more like this. So we are seeing this particular face like this. So we see that there are some CNTs which are pulled out. So CNT pull out, it means that we are fracturing the CNT. We are fracturing the CNT, and since CNT have such high strength, basically now more energy is required to break them. So therefore, now material absorbs much more energy to break the CNT. So we are achieving fracture toughening via the various methods such as crack bridging, splat bridging, pinning the cracks, and also providing a contour tortuous path. Additionally, we can also achieve it by CNT pull out. So we are seeing that CNTs have now to be broken so that a material can fracture itself. So that's what we are seeing out here, that CNTs will basically being pulled out from a surface. So we had HS surface, hydroxyapatite surface, which has been fractured. So we have fractured surface, and we can see CNTs which are coming out as a pull out from the particular surface to impart much more toughening to the hydroxyapatite crystal. So the fracture toughness becomes a particular way of evaluating the mechanical property of hydroxyapatite. So we see that once we have hydroxyapatite only, it will show a certain level of fracture toughness. If we take a fracture toughness of only hydroxyapatite, it will show certain value, and with the addition of CNT, it goes to approximately double. So we had hydroxyapatite plus some CNT, is approximately 4 to 4.8% carbon nanotube. It will approximately double the fracture toughness. And since these coatings are very porous, the fracture toughness of this hydroxyapatite coating can be to the order of around 0.3 to 0.4 megapascal root meter, because we need also these coatings to be very porous to assist with the biological compatibility, so that cells can grow onto it. And with HA plus CNT, it can grow as high as around 0.6 to 0.8 megapascal root meter. But ideally, people have seen, ideally it has been observed that 100% dense hydroxyapatite can be it can have fracture toughness as high as 1 megapascal root meter. It has also been proposed in literature that if once we start adding carbon nanotube to it, it can increase the fracture toughness up to 2 megapascal root meter. So that is the values we are approximately talking about, that how CNTs can provide reinforcement in reinforcement, and then it can enhance its mechanical properties via that much order of magnitude. So if we had hydroxyapatite at certain location fracture toughness, it can double, approximately it can double with the addition of carbon nanotube into the hydroxyapatite matrix. So we have hydroxyapatite matrix plus CNT, it can improve the fracture toughness by approximately 2 times. So that is what we are seeing, that CNT is increasing the crystallinity. So we are seeing that crystallinity can also be increased by addition of CNT by approximately 30% times 30% increase. Secondly, the fracture toughness can also increase by approximately around 2 times. So that is what we are able to see with the addition of carbon nanotube. And coming to the cytocompatibility of this particular material, there are 3 criteria to it, that cell should be able to adhere itself onto the surface, and then cell should be able to proliferate, and cell should also grow itself. So we are seeing this unrestricted cell growth even near the CNT regions. So we have particular regimes where we are seeing some CNTs which are growing out here, and over that what is happening, we are seeing that cells are basically, even when we have CNTs out there, cells are able to grow. So we are seeing the cells, it is able to proliferate or grow itself more like a fibrous structure. So it is basically growing even over the CNT surface. So we are seeing that even once we have some CNTs over here, so if we had those all CNTs and all these as biological cells, which are nothing but fiber osteoblast, these cells are growing without any hindrance. So that means that CNTs are not creating toxicity. Otherwise, had they been toxic, then we won't see any fiber osteoblast growing onto the hydroxyapatite surface. So majorly we have hydroxyapatite matrix with some CNTs out here and there which are scattered throughout on the matrix, and it also appeared that CNTs are getting distributed even in the powder stage. It appears that they have some sort of a chemical affinity with the hydroxyapatite matrix itself. So CNTs they appear to have some sort of a affinity for the hydroxyapatite matrix itself. So they tend to basically disperse even just by blending, and it means that we are not doing any functionalization. We are not doing any functionalization or surface treatment. No surface treatment has been done on the CNT surface. So we are not doing any functionalization, no surface treatment of CNT, still they are getting dispersed into the hydroxyapatite matrix without any hindrance. So they are getting distributed uniformly on the hydroxyapatite surface without any functionalization. That is the reason they tend, it appears that they have some sort of a chemical affinity with hydroxyapatite surface, and that is the reason they are distributed so uniformly even after plasma spraying, and they are able to enhance the pressure toughness by approximately 2 times. And to come back to the biocompatibility part, we are able to see that this all these osteoblasts are growing on the hydroxyapatite surface, which even have CNT without any hindrance. So it means that the overall composite is not toxic. So therefore, this overall material is showing superior mechanical properties while rendering some biocompatible nature to the implant surface. So that means that this particular material can serve as a superior coating in terms of imparting superior biological response while maintaining a very high or much better mechanical properties. So what we are seeing in this particular hydroxyapatite plus CNT is that all the CNTs, they are showing some precipitation of apatite mineral onto it. So there is some sort of a barbed wire like kind of structure what we use in fences. So we see all the fences, they have wires grown all around it. So similarly we are seeing that CNTs, they have some sort of a needle shaped kind of structure which is being grown over them. So they become more like a barbed wire structure, which is appearing onto the CNT surface. So we see that we have a CNT, and then this is a CNT, and then we have some sort of a apatite precipitation. So we have apatite needles which are growing onto the CNT surface. So it means that CNTs are basically serving as a surface for apatite precipitation. So it means that they cannot be so harmful, they cannot be toxic, because they are inducing apatite formation on their surface. So we are seeing the CNT with some apatite precipitation onto its surface. So we are seeing apatite growth on the CNT surface, and a similar structure has been observed by a couple of researchers. So that means that CNTs are not so toxic while they are being embedded into the hydroxyapatite matrix. So HA plus CNT is also serving to be much more biocompatible as compared in comparison to hydroxyapatite itself. So CNT itself is not inducing any toxic effects, because we are seeing that cells are growing and proliferating. They are able to adhere onto the surface, and they are being retained even after a couple of days. So even after 5 to 7 days, around 5 to 7 days also, we see that the cells are basically there on the surface, and we are seeing this apatite precipitation onto the CNT surface, which means that CNT itself is not really toxic, and hydroxyapatite CNT is coming out to be a much superior material with enhanced mechanical properties and with enhanced biological properties as well. So that is what the overall thing comes out to be, that hydroxyapatite is a biocompatible material, which is a chemical composition of Ca10, PO4 whole 6, OH whole twice, and then basically it is basically very brittle. So we tend to reinforce it with some carbon nanotube, because the pressure toughness of hydroxyapatite is very low, order of 1 megapascal root meter. So that is the reason we want to introduce some carbon nanotube into it, so that the overall structure becomes much more superior in terms of mechanical property. But people have already debated about the carbon nanotube being much more toxic sometimes, or sometimes very biofriendly, depending on how it has been utilized. So to confirm whether they tend to be much more biocompatible in the particular work, all these coatings have been synthesized using plasma spraying, and then we have two composites, one with hydroxyapatite with CNT and one without CNT, and then we realize that CNTs are also serving as a place for apatite precipitation. So they cannot be really toxic in nature. So we are able to see that the pressure toughness was increasing to the order of approximately double. We also realized that the crystallinity of the hydroxyapatite itself can be enhanced from 50 to around 80%, and they tend to be much more biocompatible. So all this is happening, that they show increase in crystallinity, they are showing increase in pressure toughness, but without loss of biocompatibility. That is a key part of synthesizing hydroxyapatite plus CNT as a biocomposite coating. So that is the overall nature of producing these coatings on a titanium 6 aluminum 4 vanadium implant surface. so that the overall corrosion resistance can be enhanced, the overall wear resistance of the implant can be enhanced. At the same time, we can also increase the implant life because of its increased pressure toughness. At the same time, we can also make it much more biocompatible in nature, because we can also render some porosity onto the particular coating, so that cells can come adhere itself and cling onto this particular surface. So overall, we are able to see a very superior coating of hydroxyapatite with CNT by utilizing plasma spraying in this particular case. So that is the overall theme of generating all these ceramic coatings on a titanium 6 aluminum 4 vanadium biocompatible biometallic implant surface. Thank you.